The Scanning Electron Microscope. Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. The animation first shows the schematic structure from the outside. The upper part is the so-called column. It is used to generate an electron beam. The lower part consists of the specimen chamber with cover plate. In the longitudinal section, the flange leading to the high vacuum pump is visible at the bottom. Thereby, high vacuum is generated inside the whole microscope. The round specimen stage may not only be moved to the left and to the right, but likewise in all other directions. It may also be tilted and rotated. All samples to be investigated are placed on the specimen stage. To create an electron beam, a V-shaped thin tungsten wire is used, the so-called thermionic cathode. Heated up by electric current, it emits electrons into the vacuum, indicated by small dots. Below the cathode, a metallic disc with a central borehole is installed, the anode. The anode is connected with a positive pole of a high-voltage source, the thermionic cathode with a negative pole. Further necessary components have been omitted for the sake of simplicity. The strong electric field between cathode and anode accelerates the electrons downwards. These electrons are called primary electrons. They form a broad, diverging beam which hits the specimens and the stage. But this way, the beam of primary electrons is not useful yet. An electromagnetic lens focuses it finely on the specimen surface. At the point of incidence, primary electrons knock out electrons of the sample material. These knocked out electrons are called secondary electrons. Additional components are necessary: electromagnetic deflection, raster scan generator, secondary electron detector, abbreviated as SE detector, and computer with monitor. The basic principle of the scanning electron microscope is to detect the secondary electrons and use them to build up an image. To increase the number of detected electrons, a positively biased grid is placed in front of the detector. The grid attracts the secondary electrons and leads them to the SE detector. And this is the way to generate a magnified image of the sample. The raster scan generator directs the electron beam to the left rear part of the sample and stops there for a short time. The number of secondary electrons is recorded in the SE detector. The signal is amplified and displayed as a dot at the top left-hand corner of the monitor. The electron beam pans slightly to the right, stops again. The measurement is repeated. In the same way, the next points on the sample are dealt with. The principle is, many recorded secondary electrons lead to a bright image point, few electrons lead to a grey image point, and none at all to a black one. An entire row is covered in this way. Then a second row, until finally a rectangular area has been scanned and an image appears on the monitor. If not only a few but many image points are used in the raster scan, a natural-looking image of the specimen surface can be seen on the monitor. The fast electrons of the electron beam, the primary electrons, reach the surface. They knock out electrons of the specimen material. These are the secondary electrons used for image formation. What happens in detail shows a schematically drawn atom from near the surface. Just like any other atom, it consists of a positively charged nucleus and negatively charged electrons. The electrons stay in energetically well-defined shells around the nucleus. A primary electron comes from above and accidentally knocks out an electron from the K shell of the sample atom. A vacant place remains, as indicated by the yellow circle. This state is unstable. An electron from the L shell fills the gap and the energy difference is released in the form of a characteristic X-ray photon. This X-ray photon is called characteristic because its energy is quite characteristic or typical for the particular element. Now another transition follows. And finally the atom repairs itself with an electron from the vicinity, a free electron. So X-ray radiation is generated during the operation of the scanning electron microscope, namely X radiation, which is characteristic for the chemical elements present in the sample. If the energy and the intensity of the radiation are measured with an X-ray detector, then the chemical composition of the sample can be determined. Here the typical X-ray spectrum of the piece of jewelry builds up. Chemical analysis is then carried out using sophisticated methods with the help of a computer. Certain limitations must indeed be minded, but it's definitely a fine method, and above all, it is completely non-destructive, and even very small spots on a sample can be analyzed. And what has happened to the small cobalt plate, which was one of the samples? It was used to calibrate the measurement. This means to adjust it finely. The chemical analysis is finished now. Our piece of jewelry is genuine. The gold content amounts to about 70%. The balance is silver and copper.